This blob is glowing hotter than lava, and in a few minutes it will become perfectly clear and completely see-through. How do you take ordinary sand and turn it into a window you can look straight through? Glass is everywhere, in your window, your phone, your glasses, yet almost nobody knows what it truly is. And the honest answer is stranger than you think. Glass is not really a solid at all. To understand why, we have to start with the strangest recipe in all of manufacturing. It begins on a beach or a desert with the most common material on Earth, sand, specifically silica sand, made of tiny grains of quartz. This one ingredient makes up roughly 70% of all the glass we make. But you cannot just melt beach sand into a window. Pure silica is stubborn. To melt it alone, you would need a furnace hotter than 1700 degrees Celsius. That is punishingly hot and wildly expensive. So glass makers cheat with two secret helpers, so we mix in 2 more powders and the whole recipe comes together. 3 humble ingredients that together become glass. The first is soda ash. It lowers the melting point of the sand dramatically. Add it in, and the whole mixture melts hundreds of degrees cooler, saving enormous energy. But soda ash creates a problem. On its own, it makes a glass that slowly dissolves in water. A window you could literally wash away, so we need a third ingredient to lock it down. That stabilizer is limestone, ground from ancient seashells and stone. Limestone makes the glass tough and stops water from ever attacking it. Sand, soda ash, limestone. That simple trio is the backbone of almost every window and bottle on Earth. Now these powders are weighed, mixed, and poured into a furnace that never ever sleeps. Some glass furnaces run non-stop for 10 or 15 years, without cooling down once. Shut one off, and the glass inside would freeze solid and crack the furnace apart. Inside, the heat is almost unimaginable. Inside, the batch is heated toward 1500 degrees until it glows white hot. The sand grains soften, then slump, then melt together into a thick glowing liquid. It looks like honey made of light, bubbling and folding in on itself. Tiny bubbles rise up and escape, in a slow stage called fining. Get this wrong, and the finished glass is full of trapped bubbles and streaks. But get it right, and what pours out is clear, molten, and ready to be shaped. And here is where we hit the single hardest problem in all of glassmaking. How do you make a sheet of glass that is perfectly, impossibly flat? Flat enough that when you look through your window, the world does not bend or ripple. For centuries, this was almost impossible. Glass was cast onto tables, then ground and polished for days. It was slow, brutal work, and it wasted half the glass. Windows were a luxury of the rich. Then, in the 1950s, a British engineer named Alastair Pilkington had a strange idea. What if you never touched the glass at all? What if you floated it on liquid metal? The idea sounds insane until you see it laid out. Glass on top, liquid metal below, perfectly flat. The molten glass is poured out onto a long, shallow bath of liquid tin. Tin is the secret. It melts easily, yet stays liquid across a huge range of heat. And crucially, molten glass floats on top of it, without ever mixing in. The glass spreads out across the metal, exactly like oil spreading on water. Gravity pulls the tin dead level, and the glass on top becomes just as flat. The top surface is smoothed by gravity. The bottom is smoothed by the mirror of liquid metal. No grinding, no polishing, just 2 perfectly flat surfaces formed by physics alone. This is the float glass process, and today, almost every window on Earth is made this way. As the ribbon of glass floats along, it slowly cools and begins to firm up. By the end of the tin bath, it is solid enough to lift without leaving a single mark. But you cannot just let hot glass cool in the open air. That would be a disaster. Glass hates uneven cooling. If the outside cools faster than the inside, it builds up hidden stress. That stress is a trap waiting inside the glass, ready to shatter it at the lightest tap. So the ribbon travels into a long tunnel oven called the annealing lehr. Inside the lehr, the glass is cooled slowly and evenly over a carefully controlled distance. This relaxes the glass, releasing the stress, and leaves it calm and stable. Only then is it strong enough to be cut, handled, and shipped. Diamond wheels score the ribbon, and it snaps cleanly into giant, flawless sheets. So now we have our window, but we still have not answered the real mystery. What exactly is this stuff? Is it a solid or is it a liquid? Because the truth is, glass is neither and both at the same time. Think about ice. When water freezes, its molecules lock into a neat, repeating crystal pattern. Almost every solid does this. Metal, salt, sugar, rock, orderly grids of atoms. But glass does something bizarre. When it cools, its atoms never line up. They freeze exactly where they were floating, in the messy, random tangle of a liquid. The glass sets solid, but on the inside, it still has the structure of a liquid. Scientists call this an amorphous solid, a liquid frozen in place. Picture the two side by side. One, an ordered crystal, the other, frozen chaos. It is sometimes called a supercooled liquid, cooled so fast it forgot to become a proper solid. This is why glass is clear. With no crystal grains to scatter the light, it passes straight through. Now, you have probably heard a famous story about this, that old church windows are thicker at the bottom, because glass is a liquid that slowly flows downward. Over centuries, the story goes, it oozes down like incredibly slow honey. It is a wonderful idea, and it is completely false. Glass at room temperature does not flow, not over years, not over centuries, not even over millions of years. Those old windows are uneven because of how they were made, not because they melted. Early glass makers spun molten glass into discs, which came out thicker on one edge, and builders simply set the heavier edge at the bottom. Mystery solved, no flowing at all. But if you want to see how strange glass really gets, you have to break it. Take an ordinary sheet of glass and heat it back up until it is nearly soft. Then blast both surfaces with jets of cold air all at once. The outside cools and hardens instantly, but the inside is still hot and wants to shrink. As the core finally cools, it pulls inward, squeezing the hard outer skin into a state of tension. Now the surface is locked under compression, gripping itself with tremendous force. This is tempered glass, and it is up to 5 times stronger than ordinary glass. It is what protects you in car windows, shower doors, and phone screens. And when it finally does break, it does not form razor-sharp shards. All that stored energy releases at once, and the whole sheet crumbles into tiny blunt pebbles. To see this force at its most spectacular, glassmakers have a party trick, centuries old. They drip molten glass into cold water, and it freezes into a tadpole shape with a long, thin tail. This is a Prince Rupert's drop, and it hides an almost unbelievable secret. The bulbous head is so strong, you can smash it with a hammer, and nothing happens. You can strike it, squeeze it, even shoot it, and the head simply shrugs it off. But the tail is its fatal weakness. Snap the very tip just barely, and the entire drop explodes into powder in a shockwave faster than a speeding bullet. The stress trapped inside from that fast cooling unzips through the whole thing in an instant. It is the exact same hidden stress the annealing layer exists to prevent. Now, windows are only half the story. What about bottles and jars? These are not floated or rolled, they are blown by a machine thousands per minute. It starts with a glowing blob of molten glass, cut to an exact weight, called a gob. The gob drops into a first mold, called a blank mold. There, a puff of air or a metal plunger forms a rough hollow shape and the bottle's neck. This half-formed piece is called the parison, and it already has the finished opening. The parison is flipped into a second mold, the blow mold, shaped like the final bottle. Then compressed air blows it up, like a balloon, pressing the glass against the cold mold walls. In under a second, a shapeless blob has become a bottle. This is the machine. Those bottles then pass their own annealing layer, cooling slowly so they never crack in your hand. And glass has one more quiet superpower. It can be melted and remade again and again forever. A bottle you recycle today can be back on a shelf in as little as 30 days. Unlike plastic, glass never wears out. The same atoms can become a new window 1,000 times over. From a handful